Hi guys, and welcome back to Matthew Wister. Today we're going to be talking about redox reactions in chemistry. First of all, let's talk about what a redox reaction is. Well, a redox reaction is very closely similar to a single replacement reaction. In a redox reaction, you involve oxidation and reduction. And in a single replacement reaction, you will involve one element that replaces another in a compound due to reactivity, where the one that's more reactive replaces the one that's less reactive. And it's also similar to ionic compounds, because in ionic compounds, you're typically transferring electrons from the metal to the nonmetal. So, what's similar about these two is that they both involve the transfer of electrons. However, in a redox reaction, again, we need oxidation and reduction. And there's an acronym to remember this, which is called OIL-RIG. OIL stands for oxidation involves losing electrons. And when you lose electrons, you're losing that negative charge, making you more positive or becoming a cation. Then there's reduction, which aligns with RIG, which stands for reduction involves gaining electrons. And when you gain electrons, you're becoming more negative, thus becoming an anion. However, there are some rules that are involved when you talk about redox reactions. So I'm just going to list them out. Rule number 1. All three uncombined elements have a charge of 0. So that means, let's say in an equation, right, you have, let's see, Ag plus insert some compound, right? Ag, which is by itself, it's uncombined, it's going to have a charge of 0. And the charge is associated with its oxidation number, which you mentioned in rule number 2, which says charges of ions are their oxidation numbers. Now, oxidation number, or oxidation state, just shows how many electrons an atom loses or gains when it breaks or forms ionic bonds. And it's used to track electrons in a redox reaction and determine what's being oxidized and reduced. Rule number 3. All chemical compounds except polyatomic ions are electrically neutral. The reason being is because the sum of the charges equals 0. Rule number 4. In a polyatomic ion, the sum of its atoms' charges has a net charge. So instead of a chemical compound where it's electrically neutral equal to 0, in a polyatomic ion, the sum of its atoms' charges has a net charge. And you can find this in the selected ions forming aqueous solutions table, which is in your reference table. So if I were to give you an example in your reference table, if you look at nitrate, right, it says NO3, and there's a negative sign on top. Remember, there's an invisible 1, so that means that the net charge would be NO3 negative 1. So when you're solving, it's going to be, the sum of its charges is going to equal to negative 1. Rule number 5. Hydrogen is almost always positive 1 or plus 1 when found in a compound. And that's typically because it's found in group 1, and it has a charge or oxidation number of 1. Similarly, Rule 6 says that group 1 metals are always plus 1. And then Rule number 7, oxygen is almost always negative 2 when found in a compound. Then Rule 7, oxygen is almost always negative 2 when found in a compound. The reason being is because oxygen is found in group 16. And in group 16, if you take the second digit of that number, which is 6, that means that you're going to need 2 valence electrons to achieve a full octet shell reaching stability. Therefore, it's going to need 2 additional electrons to have that full valence shell of 8 electrons, or an octet. Lastly, rule number 8. Group 17 elements are usually negative 1 when found in a compound. Similarly to my previous explanation, since group 17, the last digit of that number is 7, it's going to need 1 more valence electron to achieve that octet shell because 7 plus 1 is 8. So it's going to need 1 more electron to reach stability. Now let's get into our example, which involves copper and silver nitrate. So here we have an equation, right? In our reactant side, we have copper plus silver nitrate, and then the products, which is silver plus copper nitrate. Now what's happening here is clearly a single replacement reaction. Why? Because we see that copper, which was initially by itself, now replaced Ag, basically kicked it out, and it's now bonded with nitrate. Now here on its own, with silver nitrate, we have an ionic compound. However, when we add copper into it, copper ends up taking silver's place and forming a new ionic compound with nitrate. This is also a redox reaction because electrons are transferring. So let me just explain that part really quick. So if you look back at our rules, right? Rule number 1 says all free uncombined elements have a charge of 0. Now here, we see that copper is free and uncombined, and Ag is also free and uncombined, which is why it has a charge of 0. We see that right there. But now, in silver nitrate, we have Ag and NO3. So if we split it up, it's gonna be equal to 0. The reason being is rule number 3. All chemical compounds except polyatomic ions are electrically neutral. So since this is an ionic compound, it's going to be equal to 0, right here. Now, although we don't know what the oxidation number of Ag is, we do know what the charge is for NO3. Why? Because it's a polyatomic ion. And when we look at our table, NO3 or nitrate has a charge of -1, which is where the -1 comes here. Now, only paying attention to the charges, right, they have to add up to 0 because the sum of its charges has to equal to 0. It has to be electrically neutral. So if we have a -1, what can we add to that -1 to give us 0? It would just be a +1 because it reverses that. It cancels it out. Therefore, Ag is going to have a charge of 1 because 1 plus -1 or 1 minus 1 is going to give you 0. So now Ag is going to have a charge of +1 or +1, and NO3 is going to have a charge of -1. Now, this charge for nitrate, it always stays the same, right here, because it is a polyatomic ion. So its oxidation number does not change. Now let's look at this side here. We have Ag. So after the single replacement, Ag has been kicked out. So now it's one of the free uncombined elements, which again is associated with rule number 1. So now Ag has a charge of 0. But now we have copper nitrate, our new compound. So if we split it up, Cu plus NO3. This is, again, a chemical compound. So it's going to be electrically neutral equal to 0. NO3, once again, stays the same with a charge of -1. Copper, we don't know. However, we do know that the sum of these charges has to be equal to 0. So, again, if we have a charge of 1 or +1, it's going to cancel out with the -1. So copper is going to have a charge or oxidation number of +1. So we see this here. So we see the inner reactants, right? We start off, copper is at 0, but then the replacement after the redox reaction, copper ends up having a charge of +1. So what's happening is that copper became a cation. It lost electrons, becoming positive. So this is oxidation, because remember, oil losing electrons becomes more positive, becoming a cation. But now if we look at Ag or silver, we can see that Ag went from +1 to 0. So Ag gained electrons because it went from a +1 to a 0. So it's no longer positive. And then, as I said earlier, NO3 or nitrate, it stays the same because of its net charge, according to this rule right here. The sum of its atoms charges has a net charge, so that does not change. Oh, and I don't know if I clarified this earlier, but the reason why copper was able to replace Ag in the compound is because if you have an activity series, which I'm going to put an image of right now, Cu is higher up, so it's closer to the most active level. It's more active than silver, which is below, which is closer to the least active.